Welcome to School of PE podcast. I'm your host, Chris Miller, and I'm so glad that you could join me this week. We are going to discuss topics about FE, PE, and SC, and we're also going to answer questions that will help students prepare for their exams. Let's get started. Hello, everyone, and welcome back to another exciting episode of the SOPE's weekly podcast. I'm Chris Miller, and today we got a returning guest, Brian. Welcome back to the show. How are you?
Thanks. Excellent. Glad to be back.
Yeah. Hope all has been well. Looks like today we're going to kind of talk about some precast concrete fabrication, design, and concerns. Hard to believe that'd be concerns with something that's prefabricated, but I think we'll hear about those. So, just to kind of, I guess, get everyone else caught up to speed or back up to speed, can you let's do a recap. So what is precast concrete?
So the way we talked about it last time, most simply, is massive Lego pieces made out of concrete. So we prefabricate all the concrete in sections that you can ship and you can lift with a crane, and we send them out to the job site and weld them together, and lo and behold, you've got yourself a structure. That's precast is simply.
That's like a prefab 101. So I know I'm going to get sidetracked. I usually don't get sidetracked this soon into an episode, but I'm going to go down this path now that, you're talking about these, giant Lego pieces that you kind of ship to wherever they have to go. You weld them together and you weld them and put them together. So now I'm kind of thinking, what can't you build with it? Like, are there certain structures that right off the bat that there's no way this is going to work?
Well, that's a great question. We've talked about when shipping gets too large, when there's a product that you need that you can't put on the road, you can ship by rail and you can ship by barge. I actually did some, fairly, easy calculations on what size concrete we can ship on a barge. We had a project once that they wanted to kind of prefabricate foundations, which, isn't very normal, which are of course massive. Right. So that's probably something that would go into the realm of you really don't do, but there are means to ship these larger precast pieces.
That's a good point. And then I promise I'll get you back on track here. Last question. So let's say I want to put a baseball stadium together.
Sure.
Can we do it your way?
We can do it. We can do it the precast way. Yeah. A lot of the structure could be precast, maybe not all of it. The roof pieces could be precast. It might be a little more difficult. The risers, the stadium at which you sit on, that's easy. Piece of cake. We do that all the time. If you have any columns that you need or beams to hold up the risers, of course, that's bread and butter there too. The roofing system could get a little creative, I guess you could say, but that might be by another trade if it gets a little too complicated.
All right, that's fair enough.
If there's a roof. If there's even a roof, a lot of stadiums don't have roofs.
That's true. If we open up one in downtown LA, we could probably go roofless.
Exactly.
So you've seen the Rams football stadium. What is that? I think it's called SoFi Stadium out there in Southern California. You ever seen it maybe on TV?
No, I haven't.
I was going to say, is that something that we could do but I guess next time take a look, and then episode 3, we'll be able to talk about rebuilding the Rams stadium without building it. So what is it made out of and how is it made?
So we had a discussion last time what cement is. So, of course, precast concrete is made of cement, gravel, sand, and maybe some chemicals that'll help it kind of bind differently or more quickly and cure quickly. So that's concrete. That's what we call that mixture of materials. But also, we talk about welding the concrete pieces together. You can't weld concrete to concrete. It doesn't really work that way. You've got to cast in some embeds, and these would be steel plates with maybe some studs on them or some deformed bar anchors or DBAs, a different variety of attachments, different types of plates. There's also inserts because you've got to lift the concrete. So you can get a lifting eye into the concrete and kind of scoop the concrete up. You can put inserts in. You can put threaded inserts in if you want to do a bolted connection. All kinds of different things go into the product depending on how we design it. And other than that, you've got a lot of reinforcement.
Mm-hmm. So, I remember from last episode, I found out that I'm probably not alone in the whole concrete's the same as cement discussion. So I was glad to find out that maybe the population that thinks that is larger than I originally thought. So I'm assuming that there's some kind of curing process.
Yes, we use type 3. We use type 3 cement, which is the fastest curing, common concrete, or excuse me, cement. So we use the type 3 cement that goes into our concrete. Now we have these, what we call our beds, or these large structures. It's kind of like a bed made out of steel that could be several hundred feet long. Some of these beds are heated, so you can heat your concrete while it's curing overnight, and you can pull it out of the form in a number of hours. 8 hours might be the minimal for some, but maybe 12 would be more typical.
Interesting. So what happens after it's cured?
So after it cures, and we know it's finished curing because we have a system in place that sends all the information to the computers. And we have a little cylinder in the lab that has the exact temperature as the concrete in the bed. So that cylinder, we can monitor and say the cylinder is cured, therefore the product is cured on the bed. And then you can, cut everything loose and pull it out of the forms with a crane.
Interesting. We'll have to get more into that, but now my mind is piqued a little bit. So last episode you had mentioned the floor bending into like frowny shape faces, or frowny face shape. What the heck is that?
So that's absolutely on purpose. And the best way to think about it, we'll start by why we might do that. So if you've got a frowny face shape here like this, think about if it bends, it eventually gets straight. So when you add load, it'll straighten. Now, if you started straight and you add load, it'll turn into a smiley face, which, would look like a failure would be coming. So that's one just quick, easy way that I like to describe, why we might do that. It adds some good strength and also helps prevent cracking with large loads.
It seems as such a simple explanation. It tells the story, though. I mean,
exactly.
It absolutely makes sense, right? You start like this, you're gonna, that's not good. So no, I like it. So how do you design a precast structure? Is it something that a few people can do, or do you need to have a large team? And who comprises of that team?
Yeah. So the way we typically do it is depending on the size of the project, naturally. Most projects will just require one of us engineers. Most projects will require one lead draftsman who draws the entire building.
Oh, wow.
They draw it. Yeah, we have 2D and 3D software. So that draftsman will be working on the project, adding the connections, drawing each piece to the correct size. The thing they don't do is add the reinforcement for very particular details. Then once the buildings, we submit all of our approvals and get it moving along, with the architects and whatnot that we spoke about last time. Then the drafters come in that draw every piece of reinforcing. They dimension absolutely everything, the blueprints for the workers in the plant to produce this product. We might have 5 of those working on a project just to meet the schedule, like we talked about last time. I'd say, a crew of 7, maybe even, 5 or 6 could get the job done.
No, that makes sense. Thanks for sharing this. I got another question, sidetrack question.
Sure.
It's this whole precast, pre-created versus creating. So let's say we're building a wall structure around a building kind of like you're building like a castle has an outer wall, right? And then it has a moat, drawbridge, all that fun stuff. So let's say you're gonna build that wall around that castle, and we have 2 ways to do it. One, you can maybe bring the pieces, weld them, and throw them up, right? Sure. Or you can maybe build the walls from scratch, maybe while you're out in the field. Is that a possibility?
You can, yeah. That'd be the cast in place version we talked about last time.
Okay.
Of course, there's the advantages and disadvantages, which would be similar. If this castle is out in the boonies and maybe it's on an island, that would be way easier to just do a cast in place, because you can kind of create a little manufacturing facility on said location and just cast the wall right there, as opposed to flying it via helicopter or something. There are some limitations with the shipping, of course. And I think that would be the biggest play for when maybe cast in place would really take hold in a situation like that.
No, I got scenario B coming up.
Okay.
So we decide, so at least sometimes when you plan or you build things, they don't always go according to plan, or maybe something breaks, and you have to start over again, right? So if we're going to pour our own wall and build it up, if you mess up, you can start over, right?
You can.
But if you bring in the pieces, you've flown them in by helicopter, are you also bringing spare pieces?
No, so we definitely don't make spare pieces. Of course, that would be assuming something's going to go wrong before it happens. But there are procedures in place to make sure that that doesn't happen. The quality control procedures start, before the concrete's poured, way before, and then right before the concrete's poured, after the concrete's poured, when it's on the truck, and then we've got a guy in the field checking them when they arrive, making sure things are at least square and the right shape. So that shouldn't happen. And if it does, of course, we can manufacture another, or if it's just a minor, cosmetic thing, we can fix a lot of that. Or if a plate is missing, you can always add a plate with drilling and epoxying and something in. It'd have to be pretty major to do a new piece.
Okay. Well, you helped my story, so I appreciate that. So with the precast structures, you have your team, you have the person designing or drawing. So where do you start and what are you designing for?
Geez, so sometimes it's hard to figure out where to start, A lot of the times I like to start, a day I go through these architectural drawings. I start with getting the vision in my head so that I can talk about the project without looking at the drawings. That's always step one for me. And I like the team to do the same thing. Just spend a day or two, get really familiar. And then it comes down to the loads. So what kind of loads do I have going on here? Is this in a really heavy wind area, or is this in a seismic, active area? What type of lateral force resisting structure do I have? Do I have shear walls, which are great? Do I have just columns that might be cantilevered, kind of imagine on stilts? That would be very, very challenging. What type of system am I going to have to, stop these forces from the earthquakes or hurricanes? That's always where I'm going to start. From there, I'll kind of choose, pick my poison. I usually like to do the hard stuff first so that I can get it out of the way, which is usually the lateral force resisting system. Unless we've got some really heavily loaded floors, like we talked about with pools and hot tubs and whatnot, I might start there just to nip any problems before they become problems. So I guess it would always start with that. And then the drafting team, they start from the ground up.
Okay.
They'll lay down the foundation, lay down the grid lines on CAD or modeling software, and kind of go up from there. And they end with connections typically.
Okay, that makes sense. So how do the precast members connect to one another?
Yeah, so welding is a very common one we've kind of touched on. You can use different size plates to weld between the two. So you can imagine you've got this precast member and this precast member, and weld between with a plate. You can change the thickness, change the size of those plates. You can hide those plates by recessing the embeds and then covering it up with grout later.
Okay.
You can bolt connections. We can cast in nuts. We can cast in threaded inserts that we talked about. And then you could use kind of the grouted method. You can have some projecting rebar that goes into a tube with a hole that pops out. This is being very simplistic, but you can then put a bunch of, flowable grout in the tube, and then it hardens and it binds the two together like really strong glue.
Like some Gorilla Glue.
Exactly.
So I guess with just about anything, there can be some problems, right? Kind of made my whole thing with the whole building the castle. If you're missing a piece, what do? You can, if you were pouring it, you could pour another one. So what are some common problems with precast concrete? And then, how do you solve them?
Yeah, so we kind of touched on a lot of the limitations with shipping. One of the things I like to think about is you've got this concrete wall panel. Maybe it's 50 feet long, 12 feet wide, 8 inches thick. It's a big wall panel, and it's bouncing on a truck down the interstate, going over these bridges. We all know how it is going over the bridges. So, we've got to design for that. When we talk about designing the building, that's one thing, but you've also got to design for the shipping of the product. And then you've got to lift this wall panel that's on a truck, and you've got to make it vertical. So you've got to tilt it up, and that puts some serious force on the product. And that could cause major problems if it's not really accounted for. You can get the panel, it could crack right there before you even put it in place. Worst case scenario, this has never happened for me, but it could crack right there and break before you even put it up. there's a lot of things that we really have to pay attention for with precast, with shipping and erecting. Another thing is the precast panels, there's a joint between them. A lot of times that could be a really big argument to want to use cast in place, especially if it's an insulated structure. We discussed refrigerated warehouses, or maybe even frozen goods. How are we going to get past that? There's different types of caulk, different kinds of sealants that can be put in there. That's typically other trades, but that might add an additional cost to the overall project that, could be a big disadvantage for the precast in that field. We can make our joints smaller, which then makes us it's a little tougher to produce, because now you've got to be extra perfect.
Correct.
So there's definitely challenges along the way. And that's just a few that I can think of right offhand.
All right. So I'm assuming that you've played with Legos a time or two, right?
Oh, sure. My son plays with them too.
And maybe we can even relate this to putting puzzles together. Is sometimes you have a vision or an idea of what you want to build with these Legos. And sometimes when you go to put what's in here onto the Lego plates, they don't always connect or come together. So do we foresee any connection alignment problem possibilities?
Yeah. And I don't want to say it's common, but it happens here and there. And what do? You've got these wall panels that are right next to each other. You're supposed to weld them together. And one of the plates are here and one of the other plates is like down here. You can't weld those two together, of course.
Right.
So, a repair would come into play for something like that. You could drill an epoxy. We usually use, fairly strong epoxy for tension and shear, and put in a new plate. So you'd kind of have two plates at the location, the repair in the correct location, and then an extra one just not where it belongs below it. That'll happen here and there. And there's other repairs if you wanted to design the connection for a strap plate that might go diagonally between the two. That's going to be a weaker plate because it's spanning a much further distance to go in that diagonal direction, but you could also do that.
Okay. So I'm trying to so shipping, we talked about there can be some issues where you can only, ship certain, up to certain sizes, and then you have to determine whether you're going by rail, barge, whatever it might be. So let's say we have some precast concrete walls that we're shipping, I don't know, maybe from Midwest to LA, and we're traveling by truck. And there's some bumpy roads in between Chicago and LA. So as this concrete is sitting in the back of a truck bed, there's a lot of bouncing going on. So how much give what's built in to ensure that those bounces just don't eventually lead to where it just goes kaput? How much can it withstand?
Well, the wall panels are pretty rigid. They can handle quite a bit. Now, when they do get to the site, I talked about there's a quality guy there waiting for it. He's going to check the panels out before they do really anything with them. Give it a once over, maybe a twice over, and see what, especially if it's a long haul. Now, if there is a crack, what are they going to do about it? Depending on the size of the crack, each project's going to have a different spec. They're going to call engineering and say, hey, we've got some cracks after shipping. What should we do with them? Of course, depending on the panel type, the job it's performing on the project, you could just rub the patches or patch it over the cracks, because it's really just to make sure that no liquid gets inside to corrode your reinforcement. But if they're large cracks, we do what's called injecting the cracks. It's actually magical to watch. You put a bunch of, best way I can describe this is like syringes. You drill them into the concrete, and then you inject into these syringes a very flowable material that will literally follow its way into the cracks and fill them all up. And then once it's done, it'll start kind of shooting out of the other syringes. And when it starts shooting out of the other syringes, you plug them until all the syringes have the material flowing from them, and you've plugged them all. And then the crack is fully filled.
That's interesting. When you say syringes and injection, I'm thinking of a turkey, like you're getting a turkey ready for the deep fryer.
It's just like that, but concrete.
So what about when it comes to rigging? Like when you go to build, maybe you're doing a parking garage and it's multi-level. Maybe there's, 6 floors to this parking garage. So I'm imagining a crane's probably going to be involved, right? So what happens when these pieces are kind of twisting in the air, turning in the air? I guess I'm getting at how much risk is there involved in that when you're just, trying to lift and put things together?
Honestly, once it's in the air, as long as they're following all the procedures with the wind and he's certified and all that, once it's in the air, there's usually not many problems. Getting it in the air is the first trick, because you've got to tilt this panel, and you've got to lift it. It's on its face. You got to come up and then tilt it all the way over, and then take your rigging and put it on top so you can lift it straight up. That's the complicated part.
So it's like I'm seeing it like this. So you have your concrete flat like this. It's maybe on the bed of a big truck, right? So now you got to get it to go this way, right?
Correct.
How is it not breaking somewhere along from here to here?
That's the trick. with the reinforcement that we put in and the location at which we put these lifting devices really changes everything. You got to check the moments in between the lifting devices, check the shears at the locations of the lifting devices, and make sure you've got what you need there. A lot of times designing these panels is for lifting in the construction phase. Because if the panel's not doing a lot of work, if it's in an elevator tower,
right,
and the elevator is just hanging from a hoist, it's not technically connected to the wall panels just by maybe a rail to guide it in the right direction. These panels aren't doing a lot of work in their final stage, so they're purely designed for flipping them, just like you discussed, which is a challenge. If you've got kind of a weird shaped piece, what do you do to get this to work? I mean, you could spend a day just figuring out one wall panel. How am I going to lift this? It can be quite challenging.
It's it's kind of like we're talking about flipping. I'm thinking about an omelet or a pancake, right? And even with like a pancake or an omelet, the position and where you put the spatula to flip it is pretty important. So how important is the location of these devices on the walls?
Very important, yeah. And then also at the same time, the instructions given to the riggers to know which points to connect to. You typically have 8 inserts in the face of the panel when you're going straight up. Mm-hmm. So it'll connect to 8 of those. And then you have 2 to 4 in the edge so that when it goes straight up, it'll go there. So you might want to connect to the first 2 and the 4th and 3rd lifters and the top ones. So that'd be 8. You'd be skipping a set. Depending on the panel and depending on the moment and depending on when the rebar is developed and whatnot, that instruction alone could be it. If they follow this, it's good, and if they don't, they're going to have a problem.
Have you seen it where one is kind of bad?
I've only seen it once, and it was a panel I'm just kind of describing, kind of like an elevator pit. It wasn't doing any work in its final position, but it was a doozy to get into that position. And it had some trouble. It kind of had a shape of a banana when it was up. It really bent a little.
So is there anyone so you have someone that's attaching the connectors or the devices, right? Is there anyone else checking to make sure that they have been put in the right place, or is it just on the person doing the connecting?
Yeah, we've got the guy on site, and he doesn't do. This is kind of funny to say. He doesn't do any work. He's making sure that everybody that's doing the work is doing it right, and that's really important. And that's for sure. That's very important work.
So we've had some fun talking about concrete, prefab, and all that good stuff. But now let's get into some, I don't know, maybe a little more relaxing questions for you.
Sure.
So how many projects maybe in a given year are you designing?
That's a great question. So it does vary naturally, but I might work on somewhere between 3 to 5 projects in a year. If they're small, I'm just typical projects. If I get a bunch of small little warehouses, I can do a whole lot more. But if I'm getting a bunch of parking garages or a stadium riser job or something, I'd say somewhere around 5 would be about right.
Okay. So on the scale of difficulty, where do you rank designing and erecting the parking garages?
Well, it's funny because you think all parking garages are the same, mm-hmm. And they are for a large part, but there's always something on each project. So I want to say that they're kind of easier because you get a lot more practice at it. But then when you get that little difficult, situation on your deck, it really kind of puts it in the middle, I'd say.
Okay.
There's a lot of structures way harder than a parking garage. You've got, the tornado shelters that we talked about,
Right.
but then there's a lot that are a lot easier too. Because think about a school. It's not that high if it's just one story, and it's just wall panels maybe, and those are really easy, of course. And then you get the warehouses. Depending on how many stories, they're pretty easy. So I'd say garage is probably in the middle.
Okay. And so, you say they're very similar, where there's maybe a slight, so what do you usually see as the common denominator when it comes to what makes, parking garages different from another, I guess?
Yeah. A lot of times it's the discontinuity in the lateral force transferring system. So we talked about somebody put a stair tower right in the middle of the building instead of out on the edges.
Right.
That ruins everything. Or if you get just a funny shape, and it really just changes the dynamic of how these forces flow through the building, that's going to really give you a hard time. And then at the same time, if you don't have any walls in your structure, if it's all columns and beams, it's a really open parking garage maybe, keeping that thing stable, could be very challenging. Or you've got these large spans. For example, on a project I'm working on currently, I've got columns and I got really long spans with the beams. And the architect, who are our friends, of course, they want really shallow beams. So I have no strength in these beams to what I'm used to. And that just is a major challenge that I haven't had on another project, just really shallow beams. They just want it to be very open, and it'll look great, but it's giving me a run for my money.
So, if I'm going to build a parking garage, I'm going to come to you, Brian, and say, Brian, I'm thinking of building a parking garage for my baseball stadium, and I ask you, well, what are the benefits or disadvantages of having a enclosed parking garage versus one that's open?
Yeah, a huge one is going to be ventilation. If you want a closed structure, you're going to have a ventilation system, which often means basically another elevator tower without an elevator in it, and then they'll put giant fans to just suck all the exhaust out.
Wow.
It's pretty uncommon to have it really that enclosed with no other structure adjacent. It's usually enclosed because there's apartments all around it, either completely encompassing the entire rectangle or a U shape around most of it. But if you're just going to have a standalone garage, there's almost no reason to have it enclosed unless you have some really cool design on the outside that you want to show off, which would be a very expensive desire because you have to install this ventilation system, and the maintenance, I'm sure, is very important because they got to keep running.
I mean, it's funny is I never thought of that whole. Okay, I understand. You have a lot of cars either idling, driving in and out of the garage. So yeah, you would need something to draw that out. I never thought they would have to have a whole different system for that.
Yeah, if you next time you park, see how open it is, and there's a percentage of openness that you need. And if you say, "Well, this doesn't look very open," I guarantee you, there's going to be giant fans somewhere in that garage.
Now I'm going to drive around Columbus looking for enclosed garages just so I can check out their ventilation system. So thank you for that, Brian. So as we're coming to a close for today, I'd love to have you back again. I mean, this is an interesting topic that I can keep going on and on about. I know I got a sidetrack, but before we call it a day, do you have any words of wisdom you want to throw out to the crowd?
Words of wisdom. Well, if you're a student, words of wisdom is keep pushing because the end is there. And if you're in your career and haven't obtained your PE yet, and that's something that could benefit you, it's absolutely wonderful to have that. I'm working on my third one now for the District of Columbia. It just opens up doors for your company and yourself, just makes you a more valuable engineer. And if you're thinking about doing it and haven't done it, I would highly recommend it. It kind of puts you in the club.
I love it, Brian. Well, hey, I appreciate you coming back again for another episode. To everyone out there, have a wonderful week. And Brian, we'll see you again in another episode.
Thanks a lot, Chris.
All right, thanks.